The request is now targeting the stable cluster IP.
Mm.
But, as we established, this cluster IP is a fiction. It's not a real thing. It's not assigned to any physical network interface on any node. It is a magical virtual IP. This brings us to layer 3, which you said is the most technically complex translation step.
Yeah.
This is handled by the kube proxy and the node's kernel.
This is the leap from a logical address to a physical address. Our mental model here is the rule writer, rule executor.
Okay, I like that. Who's the writer and who's the executor?
Kube proxy is the rule writer. It's a daemon that runs on every node, and its whole job is to constantly monitor the API server for changes to those layer 2 endpoint slices. The Linux kernel, using its powerful packet filtering mechanisms, is the rule executor.
So when a packet that's destined for that fictional cluster IP arrives at a node, the kernel has to somehow intercept it and transparently rewrite the destination to a real pod IP from the endpoints list. Where does this interception actually happen?
It's intercepted using the kernel's network stack hooks. Specifically, if we're talking Iptable's terminology, this happens at the pre-routing chain in the NAT table.
Pre-routing, so that means it happens before the kernel even makes its main routing decision.
Exactly. It's one of the very first things that happens. The kernel sees a packet destined for, say, 10.96.0.5, recognizes that IP is part of a rule written by kube proxy, and performs a destination network address translation, or DNAT.
So the packet arrives destined for 10.96.0.5.80, and the kernel just silently rewrites it to, say, 10.244.315.8080, which is a real pod, and then just lets it proceed as if that was the original destination all along.
That's exactly how DNAT works. The source IP address is preserved, but the destination is changed under the hood. The application that sent the packet has no idea this translation ever occurred.
It's completely transparent.
Completely. Now let's expand on the two primary modes kube proxy uses to write these kernel rules.
Okay, let's start with the original one, Iptable's mode.
Right. Iptable's mode relies on writing these extensive sequential chains of NAT rules. For every single service and for every single endpoint for that service, kube proxy writes rules that, in effect, randomly select an available pod IP from the endpoint list.
It sounds complicated, a lot of rules.
It is a lot of rules,
Yeah.
and this works reliably, but it has a significant performance drawback. When you have hundreds or thousands of services, the kernel has to traverse these long sequential chains of Iptable's rules for every single packet that comes through.
So the more services I have, the longer the list the kernel has to check for every packet.
Exactly. That adds latency and CPU overhead, especially under high load. It doesn't scale well.
And this is why IPVS was introduced, right? To get past that sequential traversal problem.
Yes, IPVS mode is used for high-performance scenarios. IPVS stands for IP Virtual Server, and it's a dedicated load balancing framework that's been in the Linux kernel for a very long time. It's battle-tested.
And how is it different?
Instead of long chains of sequential rules, IPVS uses highly optimized hashing tables to look up the destination pod IP.
So it's a direct lookup instead of a linear search.
It's a hash table. It's a constant time lookup, which is a huge performance gain. IPVS also supports more sophisticated stateful load balancing algorithms beyond the simple random selection in Iptable's mode.
Like what?
Well, algorithms like least connections, where it sends the new request to the pod with the fewest active connections, or weighted round robin. It allows for much finer control over how traffic is distributed among the backend pods. The end result is far lower CPU utilization and reduced latency when you start scaling your services massively.
So regardless of the mechanism, whether it's Iptable's or IPVS, let's talk about that load balancing decision. How does the kernel translator choose which pod IP to forward to when there are, say, 5 pods in the endpoint slice?
In the older Iptable's mode, the selection is generally random across the available pods. In IPVS mode, as I said, you can configure much more deterministic policies. The key is that this decision, this kernel-level load balancing, happens entirely transparently at layer 3 based on the rules kube proxy generated.
Let's revisit that critical failure story that makes this whole abstract layer so concrete, the kube proxy crash.
Right. This is a textbook example of a control plane dependency causing a data plane freeze. The story was about these intermittent 500 errors that were isolated to just one node in a large cluster.
Frustrating to debug, I'm sure.
Extremely. The investigation finally showed that the kube proxy pod on that one node, let's call it node X, had crashed. It hit an out-of-memory event, and it had failed to restart cleanly.
So the problem wasn't the network, it wasn't the application, it wasn't even the endpoint list in the API server. All of that looked healthy.
Exactly. The root cause was that the rule writer was dead. But the kernel, the rule executor, it doesn't know that. It was still happily forwarding packets based on the last known good set of rules that Proxy had installed maybe hours ago.
Oh, wow. So if a pod had died, or a new one was added after Proxy crashed.
The kernel rules on that node were stale. They were out of date. Traffic was still being DNA'd to dead pod IPs, resulting in silent packet drops and application timeouts, but only for traffic that happened to land on Node X.
That's a powerful point because it forces us to decouple our layer 3 checks from what the API server tells us. The kernel's reality can be hours old.
The only way to see the kernel's reality is to query it directly on the node. The debugging signal for layer 3 is absolutely crucial. First, check the health of the proxy pod, but then you have to shell into the node and inspect the forwarding tables yourself.
Using what commands?
You'd run iptables water more nettt nat nash n, or if you're running in IPVS mode, ipvsetm nash ln. If you see stale or incorrect pod IPs in the output of those commands, you've found your layer 3 failure point.